going to start with the DGD2 today, and this will be on power transformers. So we're going to review a little basics of what transformers are, different types of transformers. So we'll probably be reviewing the basic theory that develop equivalent circuit, practical transformer, and we'll look at single phase 2 winding and then 3-phase 2 winding. Probably won't look at 3-phase 3 winding transformers because it's kind of out of scope at this point. We only need to worry about till 3-phase 2 winding transformer. And okay, so let's begin. So what is a power transformer? A power transformer is a major power system component that permits economical power transmission with high efficiency and low series voltage. It's mainly used in power generation plants where like the electricity is generated, and let's say a plant is producing 23 kilovolts, and a step up transformer would be used to maybe convert it to 2000, maybe 3000 or 7000 kilovolts. Because this is useful to do it, because as you know that uh, current is directly proportional to the loss, right? The heat loss. So that is I square R. Hence, when we have a high voltage, then the current will be low. So during the transmission line, there is less loss during the transmission, basically. Generally, power transformers are for AC voltages, and they have been utilized since like 1885, where AC power became more of a common thing to use, and the power transformers were developed. Today's transformers almost operates at 100% efficiency, and they like go beyond at least 1500 mm, megavolt ampere. So that's a lot of power there. So let's see. Then the ideal transformer. Ideal transformer below shows a basic single phase 2 winding transformer where 2 windings are wrapped around a magnetic core, and they have been wrapped around a magnetic core. It is assumed that there are transformers under sinusoidal wave, which is the AC power coming in, which is an E1 and E2. I'll explain it in a little detail. It's like E1 and E2 are the voltages across the winding. You have to remember that, across the winding. And the phasor current I1 is entering through the first side, and I2 and first side has N1 turns, and I2 is the current leaving the second winding, and it will have N2 number of turns there. Um, for the ideal transformer, we assume a lot of stuff, and I'll explain them in a little detail here. So here how general transformer single phase double winding looks like. Generally, this is from the number of winding we can see. It looks like a step down transformer. So the step down transformer is when it converts high voltage to low voltage. Generally, these types of transformers are available in at near residential area where the distribution system is like. So the high voltage is coming from the power generation plants, and then the step down transformer will be in a distribution area where they would step down the voltage, increasing the current, and then they will transmit it to the residential areas. And even some residential areas might have a smaller substation where it will be stepped down further to become to a house. Even like sometimes if you see like a pole, like especially a wooden pole with like a box on it, that's a transformer right there. So it's converting the voltage coming in from high voltage to a low voltage. That will come to your house, which will be and the large current that is generally used by your devices. And okay, so the core has core permittivity, which is mu c, then a cross sectional area AC, and then the mean length of the magnetic circuit, which is LC. And see, as you see, E1 here is the voltage across the winding, and E2 is the voltage across the winding on the other side. So, and then we'll do later questions in which it will look like something like this, but then we will have V1, which will be the source voltage, and V2, which is like the receiving end voltage, what you get at the end. All right. Okay. So and then we have the schematics of how they're kind of drawn in like a circuit diagram design way. So it looks like this. S1 is the power coming in, and S2 is the power going out on the other side. AT is the ratio between the primary winding and secondary winding. So it's generally defined in that way. We'll more look at that here. So we can see that the current enclosed like from the figure above of the thing, there's going to be a current flowing in the circuit, right? So it's going to be a clockwise current that's going to come in. It could be defined as HC times LC is equal to N1 I1 minus N2 times I2. All right. So now we assume as being an ideal transformer, we have to assume some assumptions. So the core permittivity is constant. The core permittivity remains constant, and we can define magnetic flux density inside the core as this formula: BC, which is magnetic flux density, is equal to mu c times Hc, which is times Hc, and can be represented in Weber per meter square. Sorry, 1 second, guys. And the core flux can be defined as BC times AC, which is in Weber. However, if we define, then finally we define core reluctance as LC over AC times mu c. Hence, combining like the first one and this one here, like the first one right here, combining this equation with the with this one right here, we get the following equation. So N1 L1 minus N2 L2 is equal to LC over BC divided by mu c, and which can over further be written according to this one here. You can write it as LC is equal to mu c times AC times phi c. All right, and finally we can write it in terms of just RC, which is the reluctance, and the phi c is the magnetic flux, core flux in it. All right, for the ideal transformers, we assume mu c is infinite, hence, which means that the reluctance would be, if according to the equation here, if this is infinitely large, the reluctance will be so small that it's almost negligible. Hence, we consider it to be zero. Hence, we come up with the equation N1 I1 is equal to N2 or I2, or it could be written as I2 divided by I1 is equal to N1 over N2. However, it can also be written as E1, which is the what was this? Which is the voltage across the winding is equal to the number of windings on the first side, and divided by winding on the two side, which is equal to the E2 on the other side, which is the voltage across the second winding. And as we said before, turn ratio can be defined as N1 over N2. And in terms of that, we can write, rewriting this equation. Let's say when your calculation, you're asked to find E1 voltage across winding 1, you can use the following equation here, and just simply moving E2 to the right hand side, multiplying by N1 and N2, and then replacing N1 over N2 by AT, which is the turn ratio basically. So E1 can be defined as turn ratio times voltage across the second winding. Right, and same can be done with I1 or I2, I guess. Okay, we did it with I1 here. So I1 could be same as I2 times N2 over N1 times I2. Hence, we write I2 divided by the turn ratio. So you have to make sure, just for the current, you have to be a little careful there. It's I2 divided by the turn ratio, not multiplied. And now we have power in the winding 2 could be defined as S1 is equal to E1 times I1, and then as we defined E1 earlier, which is turn ratio times E2 here, times, which is I1 is I2 over AT, which is equal to E2 times I2. Hence we get S2. In an ideal transformer, the power entering must be the same as power entry exiting the system. Hence, there is no real or reactive power loss in the system. So that's what the transformer's job is to do, like transfer that amount of power across the transmission line, and by the end of it we should have the same power, maybe a little less in real life as there are some loss, transmission line loss, heat loss, and various loss, but in ideal transformer whatever you put in should be coming out. So that's a good way to check your calculation, that the power that's coming in should always be the same as power going out. um, yeah, all right, so we can define impedance too now basically. So impedance of winding 2 of an ideal transformer is equal to, we define it's basic Kirchhoff's law, which says V is equal sorry, not Kirchhoff's law, the relation between the resistance and the current. V is equal to IR, and then R can be written as V divided by I, right, basically. So here instead of V we have E2 and impedance is Z2. Generally impedance load is connected on the on the receiving side of the transformer most of the time, and hence the load is always on that side. So we always consider a load on the second side of the transformer, receiving end of the transformer. Okay, so we define impedance just as that, and then if we were to see impedance from the winding 1 of the transformer, it's generally written as E1 over I1, which is ET times E2, AT times E2 divided by I2 times AT. Hence, it becomes AT squared times Z2. Hence, we can say, if you're, let's say the question says, find the impedance load as seen from in terms of winding 1, it's basically turn ratio square times the value of the impedance in this case. Alright, so here's an example we're going to do. It's just a basic example. We have a single phase 2 winding transformer which is rated at 20 kV, and it has a 480 to 120 volts. It's a step down transformer, 60 Hz. A source is connected to a 480 volt winding supplies and impedance load connected to the 120 winding. See, as I said before, the impedance is always connected on the 120 volt side. The load absorbs 15 kVA at 0.85 PF lagging when the load voltage is 118 volts. Assume that the transformer is ideal and calculate the thing. See, now it's asking the voltage across 480 volts. As I said, 480 volts winding is the winding 1. So that is the voltage. So we have 480 right there. But there is also a term that is the voltage, that is E1 we have to find in this case, which is the voltage across the winding 1. So we come up, we draw the diagram, the ideal transformer. We are given S2, which is what, 15,000 with an angle of 36.87. That is cos inverse of 0.8. If you do cos inverse of 0.8, you will get 36.87 here. And we are given the current I2, which is going this much, and then you're given E2. You need E2 to find E1. They have to give it to you. So when it says lagging, when the load voltage is 118 volts, that's what the E2 is. It's how much the winding is absorbing there. Voltage across the winding right there. Alright. So we go, okay, so to calculate it, so first we have to find the turn ratio, which is same as N1 over N2. But in this case, we don't know N1 and N2, but we know that they equal to E1, which is equal to E1 over E2. They're generally the rated values. You generally use on the rated values here. However, we don't know the current on each side, so we can't use I2 over I1. If we did, we could, but in this scenario, we don't at this point. So we go along with this. So E1 rated is the beginning, which is 480 volts. After that, divided by E2, which is 120 volts, which gives you 4. So now E1 is equal to 80 times E2. But we know E2 now. We were told that E2 is 118 volts, so all we do is 4 times 118 angle 0, and we get 472 volts. So that's the voltage across the winding at winding 1. Alright, so the second one was the load impedance. So we have to calculate the load impedance now. To calculate the load impedance, we know the power absorbed by the load is 15 kVA, which can be written as, this is right there, 118. There you go. So we know the power formula is E2 times I2 conjugate. We know E2 is 118, but we don't know I2. But we know the power that is being absorbed on the right hand side. So we begin with this. I2 is equal to calculate I2 is just dividing 15,000 by 118, and we get the following. So 127.12 angle minus 36.87. This is what it's written right here. So this is how they calculated it right there. And just to calculate the impedance is just E2 over I2, which is 118 divided by 127.12 angle minus 36.87, and we get 0.9238 ohms. That's there. So that's the impedance. Okay, now it's asking the question. The load impedance referred to the 480 winding. So basically from winding 1, what's the reference? How can we see it from that side? As we know, we just had a simple formula. We can just do is 80 squared times Z2, as we already calculated Z2 last time. So it's 4 square, which is 16 times 0.9238, and we get 14.87 angle 36.87. So it's that simple. And the real power supplied to the 480 winding. Okay, so here's like, instead of calculating everything again, we can just assume the power remains the same as it's an ideal transformer. So power that is received at the second end will be remain the same as the one that is being supplied from the main source, right? Winding 1. So hence we do 15,000, 36.87, convert it into Cartesian coordinates. So that is 12,000 plus J 9,000. All you have to do is just take them and separate it. The real power is 12,000 watts, and 9,000 is the VAR or kVAR, which is the reactive power that is being absorbed by the system. All right, let's move on to the next one. All right, so let's look at the equivalent circuits for the real transformers. Here. So as before we saw, the transformers didn't have any ideal transformer didn't have any resistance attached on the winding 1 side. Here it was just that, and then just a load was that is connected to the secondary side of the transformer. However, when we have a real transformer, the windings have resistance which has to be displayed, and the core permittivity UC, which we used before, is finite, and the magnetic flux is not entirely confined in the core. That means there is leak some magnetic flux that happens during the transformer, and there are real and reactive power losses in the transformer. Hence, like, the power that comes in is not going to be the same as the power that goes out because of this. Okay, so we can see here the resistance R1 is included in series with winding 1 to account for the I square R losses in the winding, because the winding has like a certain length, and then the heat loss happens because of that. The resistance X1, called the leakage leakage reactance of the winding 1, is also included in the series with this winding to account for the leakage flux that happens in winding 1. The leakage flux is the component that only happens in 1 but does not link in winding 2. It causes the voltage drop, which is I1 times JX1, which is proportional to I1, and that causes the thing to lead current by 90 degrees. Alright. Similarly, there is a resistance in R2 that we have, and a leakage reactance X2 in the series of winding 2. There you go. Alright, let's begin. Okay, 1 second here. When did this go? Okay, so now here, the figure 1, just the one right here, A, represents the equivalent circuit for a practical single-phase double winding transformer. The resistance R2 and the leakage X2 of winding 2 are referred in the winding 1 winding winding one via, no, sorry, my bad. Okay, yeah. Oh yeah, okay, so yeah. So it shows like the reactance X2 and then the resistance R2 of winding 2 is referred in terms of R1 in this figure. So it can be defined in such a way. For here, we have a much more simplified figure in which the shunt branch, the one right here, is omitted, which corresponds to neglecting the exciting current, which is the eddy current. Since the exciting current is usually less than like 5% of the rated current, neglecting in a power system is often valid, like unless useless transformer efficiency or exciting current phenomena are particular concern. For large power transformers, like which rate more than at least 5 kVA, the winding resistance, which is very small compared to the leakage reactance, can often be neglected, as we can see from this figure. Then we have finally can often like we can just like completely get rid of this. Okay, so finally we can just get rid of the get like especially for larger transformers we can get rid of the resistance here, which is like almost negligible compared to the leakage that happens during leakage reactance that happens during the power transmission. So hence we can just get rid of the R equivalent one and just have an ideal transformer like this, and it can be simplified in a certain way. And thus the like a practical transformer operating in a sinusoidal steady state is equivalent to an ideal transformer with external impedance that would be anything connected to the secondary side of the winding and admittance branches, as we can see in this figure right here. We can even evaluate the branches in terms of in terms the external branches like the one we have right here can be evaluated in terms of short circuit and open circuit test, which we'll look through an example just below. Yeah. Okay, so we have an example here. We have a single phase 2 winding transformer which has 20 kVA, 480, 120 volts, 60 hertz. During a short circuit test, where rated current is at rated frequency is applied to 480 volt winding, denoted winding 1 with the 120 volt winding 2. Shorted, and the following readings are obtained. V1 is 35 volts and power is 300 watts. And during an open circuit test, where rated voltage is applied at winding 2, the winding 1 opens, the following readings are obtained. I2 is 12 amperes and P2 is that. From the reactance, determine the equivalent circuit of impedance Z equivalence 1 is R equivalence 2 plus J X equivalence 1, referring to winding 1, neglecting the shunt admittance. Okay. As we have seen here, so we will be using this circuit right there for the test. So we have the short circuit test, basically neglecting the shunt resistance that was supposed to be in the middle right here. So we have the following diagram. We start by calculating the I rated, as we have V1 and P1 here. So I rated is what? 20 kVA, 20 times 10 to the power of 3 divided by 480. So we get 41.67 amperes basically. R equivalence can be calculated as the power that we found that is given to us 300 divided by the current. So that is current square basically. So 41.67 square, and we get 0.1728 ohms. Alright, and then we have Z equivalence. Z equivalent 1 is V over I, which is 35 volts, which is also given to us, divided by 41.67, which is 0.84. Hence, we can use Pythagoras theorem where it says X equivalent is equal to under root Z equivalent 1 square minus R equivalent 1 square whole square. So we find X equivalence to be 0.822 ohms, and Z equivalence can be written in terms of that again, and we put it right there. So we get 0.8400 to that. You can always calculate with me with the way I'm doing right now. So you can just make sure that you're kind of getting the concept of what's happening at this point. So, okay. Now the second one is when the open circuit test determines the shunt resistance, which is defined as Ym is equal to Gc minus JBM. It's referring to winding 1. So we neglect the series impedance in this one, in that one, and just follow the shunt resistance that happens right there. And so you can see Gc is the resistance minus Jm, the capacitance right there. And we begin of that, and then we have the open circuit test on the first side. So there's a source coming from the secondary winding side, basically. All right. The equivalent circuit, we begin with that. V1, as we know how we can calculate V1 is equal to E1. As there is no winding in this case here, there is nothing. This is an open circuit says, so the voltage across here would be the same as voltage across V1. So in this, we don't have to differentiate between V1 and E1. Probably going to be the same thing, just because it's an open circuit in this scenario for us. All right, so it's equal to A1 times E2, which is N1 over N2 times V2 rated. Hence 480 over 120 times 120, so which gives us 480 volts. So we get 480 volts across it. And then same thing as above, we calculate resistance as power given divided by VI square this time. So 200, instead of here, you just have to be sure that the GC is with terms of voltage, not the current. So we have a little opposition here. So we get 0.00868 S. But however, for calculating Ym, which is total one, which is can be calculated as N2 divided by N1, which is 1 over 80 times I2. So it's basically I1 divided by V1 in terms of other ways. But we don't know I1, so we have to put it in terms of N2 over N1 times I2. So 120 divided by 480 times 12 divided by 480 gives you 0.00625 S. Then we calculate Bm as the same thing as before, Pythagoras theorem, Ym square minus Gc square under root the whole thing, and you get this. And you calculate Ym in terms of Gc and Bm, and we get this thing. And we can note that the equivalent series impedance is usually evaluated at rated current for short circuit test, and the shunt admittance is equivalent to rated voltage for an open circuit test. For small variation in transformers operating near rated condition, the impedance and admittance are often assumed constant. Alright, so that's that. Okay, the saturation. So there's something that happens to a transformer. It's called like a saturation, a condition where transformer's core is fully magnetized and is producing maximum magnetic field. Excuse me. Saturation is a state reached when an increase in applied external magnetic field cannot increase the magnetization of the material further. So the total magnetic flux density B more or less levels off. So generally it's characteristics of ferromagnetic and ferrimagnetic material, generally which are used as the core for the transformer. There's a graph below we can use to see like how many turns and the magnetic flux affected eventually. Yeah, and there's something called, I'm not sure if you want to discuss this, but it's something called inrush currents. It's when a first transformer is energized, the transition current much larger than the rated transformer current can flow for several cycles. This is what you call an inrush current, is and has a large DC component. It's like a big sinusoidal thing. So I'm not sure if you should be doing this. So let's see. Yeah, I guess just know the basic. It's just like a large rush of current that happens when the first transformer is turned on. So let's not just worry too much about that. Okay, now we look at the per unit system. Power system quantities such as voltage, current, power, and impedance are often expressed in per unit or percent of specific base values. For example, if a base voltage is 20 kilovolts is specified, then the voltage of 18 kilovolts is 0.9% or 0.9 per unit or 90%. Calculations are generally based per unit quantities, but if you're going to be converting to the per base, then we have to make sure that everything gets converted into the per base value eventually. Alright, so here are some formulas that can be used to calculate the base formulas. So PU stands for per unit, I stands for per unit, and we have this here. Alright, some basic calculations we can see how it's done. A single phase 75 kVA 2000 volt 2400 to 240 60 Hz has the following parameters: RP 1 ohms, RS 0.005 ohms, XP 1 ohms, and XS is 0.0 ohms. So we know VA base is 75,000, VA secondary is also going to be 75,000, and V base is 2400 and the other one is 240. So I base can be calculated as 75,000 divided by 2400, which is 31.25, and 75,000 over 240 is equal to 312.15, so it's almost the 10 times right there. To calculate the resistance per unit, so what we do is 2400 divided by the current, that is 76.28, and just the basic simple calculation, and you get 0.7628 volts here. Alright, let's do this here. And electric load is rated at 120 volts, 500 watts. Compute the per unit and percent impedance of the load. Give the per unit equivalent circuit. P is equal to, calculated as V square over R, and R is equal to V square divided by P. Hence, we know the power and we know the voltage, we can find the resistance. We find it's 28.8 ohms. We assume the power factor to be 1 as nothing is given, so we just assume it's to be the same. Hence, the angle would be 0 degrees. Then we select some base quantities according to what we want. So we selected S base to be 500 voltage ampere, and then V base is equal to 120 volt. To compute the base impedance, we use the formula right there, this one. V actual over V base. So the per unit, compute the base impedance is VB square, which is 120 square over the power, which is 500 at this point. So we have 28.8, same thing. And the per unit impedance would be Z over ZB, which are the base values. So we have 28.8 divided by 28.8, which is 1 per unit equivalent circuit. So Z impedance is 100% at this point. So this was same because this is what we chose to base. Like some base values could be different given to you according to the questions. However, you can keep them same here. Like this was easy for a calculation, just to show like how the way it is done, as you have to calculate the base impedance too. So you can always choose something. Let's say the power given was 1200 and the voltage to given you was 200. So the difference would be a little different, and then we will get per unit impedance to be a little different, or in terms of point, basically something smaller. So then you can say it will be a certain percentage of what it is basically at that point. For us it remains the same at this point. Alright, okay, per unit impedance example with a single phase transformer. So single phase 2 winding transformer has rated 2 kVA, 480 120 volts, 60 Hz equivalent. Leakage impedance of the transformer referred to 120 volts side, denoted by winding 2, Z equivalence 2 is this. Using the transformer rating as a base value, determine the per unit leakage impedance referred to winding 2 and referred to winding 1. So we are given how the leakage winding is referred to on the winding 2 side. Alright, let's see how this we do it. So we know the base value for the transformer is given to us, which is 20 kVA, 480 volts, and V base 2 is 120 volts. So we can find Z base 2 based on that, which is 120 volts square, V base 2 square divided by 20,000. So we get 0.2 ohms. Then using the per unit impedance referred to winding 2, we know that Z equivalence 2 per unit would be Z equivalent 2 divided by Z base 2. So you know Z equivalent 2 is given to you in the equation here, which is this one, which will be divided by 0.72, which we just found right here, which is from the base values. Hence, we get 0.729 and 7.813 per unit. Now, referring to Z equivalent 2 in terms of winding 1, all we have to multiply is again is Z equivalent 2 times 80 square, which is the turn ratio square, n1 over n2, which is 480 over 120 square, and we get 0.82. And the base impedance on the 480 volt side of the transformer, we have Z base 1, which is equal to V base 2 divided by S base, which is 480 square, divided by 20,000, which we get is 11.52. And per unit leakage for the winding 1 could also be written as Z equivalence 1, which is we just found is 0.84778.13 degrees divided by 11.52, and we get 0.707929 Z equal to Z equivalent 2 per unit. So if you see this, it's almost the same. This unit is the same as the one as per unit for the Z equivalence 2. Remains unchanged and referred from winding 2 to winding 1. This can be achieved by specifying the formula right there. The V base 1 or B base 2 is equal to V rated 1 or V rated 2, which is 480 over 120. Alright. Then we have some per unit circuit of how a single phase ideal transformer looks like. Two winding transformer looks like. So ideal transformer is just no resistance. They're collecting exciting currents. We have the resistance and the impedance in series. And when the complete representation is when we have the shunt admittance, and the series admittance here. So we have both here. We can define them like E1 per unit could be defined almost the same as E2 per unit. And same can be said for I2 per unit. Can be done. Okay, then we have three-phase transformers now. Alright, three-phase transformers are mainly used in power distribution system, as we need three-phase transformer to able to step down. This is one partially true that a regular single transformers can be ganged together to perform what a three-phase triangle will do. Give me 1 second here. Sorry about that. So let's go back to it. And eliminating the requirement for a special three-phase. However, special three built for those tasks, and they're able to perform it better with like the size being smaller, and instead of like stacking three transformers on right next to each other, and they require less material to be built. Alright, so we have three transformers is made of primary and secondary winding wrapped around one leg of an iron core assembly. Essentially, it looks like a three-phase transformer sharing joint cores as we can see from the figure below. The windings here could be connected in two separate ways. One is the Y connection, the other one is the delta configuration. The various combination can be connected together and we can see how different windings have its own advantages and disadvantages. Okay, so the primary winding could be, and the secondary combination could be YY, Y delta, delta Y, or delta delta. The reason to choose configuration transformer connection are the same as any other three-phase application. Y connections provide opportunity for more voltages, while delta connection enjoys a higher level of reliability. Probably the more important aspect of connecting the primary and secondary winding together to form a three-phase bank is paying attention to the proper winding phase, polarity, and the winding here. So this is what the Y1 looks like, as it kind of shapes in a Y, so we call it Y. Here we can see all the polarity of a negative ones. They end up on the same end here. So positive on the far end, and negative one all together on one end. However, in the delta, the connection is opposite. The plus is managed by the is met by the negative on the other end of the winding, and same happens on every corner of the delta connection. means that the voltage drop here at the point at the voltage here, here, and here, it's going to be 0, as the voltage coming in, it's the one kind of like taking the voltage out at that point, so it's going to be 0 there. So I think Y is the only one that has a neutral wire in it. It's typically called the phases. So yeah, that's with junction point, although it certainly helps potential problem, but one element of the three-phase load field opens as discussed earlier. So three-phase without the Y connection here. Okay, so when we measure voltage and current in three-phase system, we need to be specific as to what we are measuring. Same as I said last time with the transformer, we have to be very specific as to what being measured and answered. Line voltage refers to the amount of voltage measured between give me a second. Yeah. Okay, so line voltage refers to the amount of voltage measured between any two lines, conductors in the balanced three-phase systems, while the above with the line voltage is, we can see the line voltage is approximately 208 volts for this diagram right there. The phase voltage refers to the voltage across any one component in a balanced three-phase system. So the phase voltage is 120 volts because this is across one component, and the line voltage that is goes along the line, it is 208 volts. Y-connected source and load always have line voltages greater than the phase voltages, and the line current equals to the phase current basically. So in Y, only voltages change, and generally line voltages are higher than the phase voltages. Balanced, the line voltage would be equal to the phase voltage times the square root of 3. So E line is equal to square root times E phase. So square root of 3 times 120 gives you 208, roughly 208. And I line remains the same in I phase. However, it's opposite in delta configuration. Delta configuration never doesn't have a neutral line to begin with, and it looks like a delta from the Greek letter, just the opposite version of it. So we have this here, and then okay, so here each pair of line conductor is across a single winding in a delta circuit. The line voltage will be equal to the phase voltage, as I said before. The one here, the coming in, is the same as going out, hence the voltage remains the same. The one that goes in here will be the same going out of here, because attached to the two node, no line current will be a vector sum of two joint phase current. Not surprisingly, the result equation configuration, we can see that E line is equal to E phase, but whereas I line is equal to the square root 3 times the I phase. So basically in this, the I phase current will be less than the current flowing through the line, as the current gets divided when it's coming into the delta connection, and it only combines when it's going out of the delta connection. So hence we can see it in two different ways. Okay. Alright, so here we can just see an example here. So with each load resistance receiving 120 volts from the perspective phase winding of the source, the current in each phase of the circuit will be 83.33 amperes. It basically can be calculated according to that as follows, which is the power, which is 10 kilovolts, the one that is being dissipated here, times it's a delta one, so the voltage in that remains the same. You have to remember that. So it's just going to be what we have, 120 volts right there, which is 83 for each load and resistor, basically. So then to find I line is under root 3 times 83.33 amperes. So we get I line is 144.34. We just assumed each unit here. So 10 kilovolts divided by 120 gives you the current in each unit or a phase, right? So we get it in a phase. So to find the line one, you just multiply it by root 3 right there. So we get 144.34 ampere. And finally, single phase transformers. Okay, so auto transformer is a one in which it only has one series of winding instead of two, as we can see from the figure below here. Connected in generally the windings are connected in a series, and hence it's called an auto transformer. The two windings are coupled magnetically. For the usual transformer, we generally have the windings that are covered to the magnetic flux or the magnetic core, but for auto transformers, the windings are both electrically and magnetically coupled. So because of that, the auto transformer has smaller per unit leakage impedance than the usual transformers, and hence we have a smaller series voltage drops, that is like in the shunt impedance and the series impedance, and a higher short circuit current though. But that's a big disadvantage for that point at this point. Let me fix that for you. And I think that's it for the DGD. I'll probably post another one. This is just like a basic going through of all the how the transformer is and what everything is. Um, I can post my document if you guys want on the slides, but like it's mostly from the textbook I take. You can always use the textbook that Prof recommends. That's what I've taken the examples from, and I'll probably give you some examples from right there to do it to begin with. So it will be a good idea to grab a textbook and see how the questions are solved and what they kind of expect you to learn at this point. So I just kind of went like overview of everything that was supposed to be done. So maybe I will post another video, just like some questions in it, and then we can solve them together. And thank you guys, and have a good day.